Hi, and welcome to my talk on CUDA.jl 3.0. I'm Tim, I'm a software engineer at Julia Computing, and I work on several Julia GPU packages and the compiler functionality that they require. Today, I'll be talking about the CUDA.jl package for programming NVIDIA GPUs in Julia. So earlier this year, there was a breaking release, version 3.0, and since then there's been many new exciting features. For example, it's now possible to use CUDA APIs for constructing computational graphs. We have a new cassette-like feature for overriding functionality with device alternatives, and that has made it possible to implement a device-side random number generator. There's also a new memory allocator that features greatly improved performance, and the QArray type now supports is-bits union element types. The most significant feature, however, touches on the programming model. It is now possible to write a GPU program that executes concurrently. But before I get to that, to concurrent computing, I need to explain asynchronous operations, which are a requirement for concurrent programs. So asynchronous operations are operations that don't block and make it possible for other operations to execute while waiting for the asynchronous operation to complete. With GPUs, many operations are asynchronous because they are executing on a different device, and you don't want to necessarily block the CPU while you're waiting for the GPU. In this example here, launching a kernel is an operation that returns immediately, so from the CPU's point of view, it's an asynchronous operation. However, before we can process the result of this computation, we need to wait until it has completed. So the call to synchronize does exactly that. It blocks the CPU until the GPU has finished executing. So it's a synchronous operation. And you can very clearly see this when profiling the code. I'm using NVIDIA Nsight Systems to do so, simply launching Julia under nsys and wrapping the code I want to profile with the add_profile macro. That produces a profile file, which we can open using the Nsight Systems user interface, producing what I've screenshotted here on the slide. The bottom lines in the screenshot represent threads executing on the CPU, and as you can see, the time spent launching our kernel is very short. The top lines represent the GPU, which takes much longer actually executing this kernel. And this is a very common pattern for GPU programmers, because these asynchronous launches make it possible to use the GPU much more efficiently. And to illustrate that, if launching a kernel were synchronous and we need to wait for each kernel to complete, the GPU will always be idle when we're launching the next kernel. And those are the small gaps in the GPU rows on top. So instead, with asynchronous launches, we can launch a new kernel while the previous one is still executing. And that effectively hides the launch overhead and is crucial to efficiently using a GPU. And here the GPU row is much more densely packed, implying the GPU is kept busy all the time. It's still not ideal though, because for one, it requires you, the GPU programmer, to take care and only use asynchronous operations. Because as soon as you use a blocking operation, like a synchronization or a memory copy, you have to wait for that operation to finish, which may take a long time. Also, at some point you do need to wait for the GPU to finish so that you can process its results. But while the CPU is waiting for the GPU to complete, it's blocked in the CUDA libraries and it cannot be used to perform other useful work. So to improve that, let's have a look at concurrent computing. This is a programming model for expressing operations that can execute concurrently as opposed to sequentially. Julia already has great support for concurrent computing. The operations are grouped in tasks, and we can create tasks using the add_async macro. We then group multiple of these tasks with the add_sync macro, indicating that we want to wait for the result of each of these tasks while they execute concurrently. So when we execute this example, we start with the first task, and when it blocks, we'll switch over to any other ready task, in this case the second task, which will print some more, and then we go back to the first task. So conceptually, these tasks execute at the same time, but in reality, we only have a single thread of execution. So we only switch to the second task when the first one performs a blocking operation, like this call to sleep here. This means that concurrent computing is especially useful with long-running blocking operations, like downloading from the internet when you have to wait for the network, or working with file system when you have to wait for the disk, or in this case, working with GPUs and having to wait for GPU kernels to complete. So that's the major change in CUDA.jl 3.0, making it possible to use GPU operations in Julia tasks. Blocking operations like call to synchronize will now give the Julia scheduler the chance to switch to another task that's ready to execute. And this greatly simplifies the programming model because it's now much less of a problem to call blocking operations while launching kernels, because this will just result in another task getting the chance to execute. Similarly, during synchronization, when the CPU is waiting for the GPU to complete, it won't just be spinning inside of the CUDA libraries, but it may be doing some other useful work on another task. Of course, this is only true when you have other tasks to execute. So let's have a look at how we can effectively use multiple tasks with GPU programming. So one possibility is to perform computations on the CPU while the GPU is busy. And we can do so simply by putting those operations in a separate task. When the GPU task then hits a blocking operation, like the call to synchronize here, we will switch to the CPU task to perform some other useful work. But there is a complication, because in the end, there's still only a single thread of execution. We only switch to the CPU task because the GPU task allowed it. And similarly, the CPU task should perform operations that still allow the GPU task to make progress. Now, many operations are like that. For example, as I've mentioned, any I/O, like the file system or the network. Synchronization primitives like locks or conditions will also perform task switches. And if you want to send or receive data, possibly from another task, you can use channels. But generally, what you shouldn't do is just perform raw compute in a task, since that will starve the single thread of execution. There are workarounds, however. You could insert a manual yield point, which will give other tasks the opportunity to execute when you call that function. It is always better to use high-level primitives like channels, but this may be a way out if there's no alternative. You could also use a dedicated thread to perform the computations on, but more on that at the end of this talk. So all this also applies to GPU operations. The GPU task should not starve the single thread of execution. However, it's much less of an issue because most GPU operations are fully asynchronous and they return immediately without blocking the CPU. So I've already shown how launching kernels is an asynchronous operation, but that also extends to more complex functionality like broadcast or matrix multiplication. In addition, most memory operations are now asynchronous too, so you can allocate and initialize GPU memory without synchronizing the GPU. Other operations are synchronous, implying they take a while to finish, and a very explicit such operation is the synchronize function, which will block until the GPU finishes executing. Some other operations are implicitly synchronizing. For example, if you copy memory from the GPU to the CPU, we will first wait for the GPU to finish to prevent reading incomplete results. But what's important here is that the blocking nature of these synchronous operations is implemented by CUDA.jl in Julia. So while your task is waiting for the GPU to finish, other tasks can execute. And all that is new in CUDA.jl 3.0, and it's crucial for concurrent GPU computing to work effectively. There is, however, something to watch out for, namely that some operations block in CUDA itself, outside of Julia's control. And when we hit such an operation, we won't be able to switch to another task, but the CPU will just be spinning. And sadly, a very common operation like that is when you're copying memory to or from the CPU. As you can see in the profile trace here, the bottom row, the CPU, is kept busy for most of the time during the memory transfer, which is inefficient. And the reason behind this is that CUDA, the CUDA library, refuses to perform this operation asynchronously because the operating system could in theory page out this memory. So it first copies all of the memory into a staging buffer before performing the actual memory operation. And that's very wasteful. The fix here is to pin the CPU memory, and this tells the operating system that this memory cannot be paged out, enabling CUDA to perform the memory operation asynchronously. And again, you can clearly see this in the profiler trace where the CPU now isn't kept busy and is free to perform other operations. It's completely idle. So memory pinning is important if you want to benefit from concurrent GPU computing. However, sadly, it's also a very expensive operation. That's why CUDA.jl cannot do it automatically before every memory copy, and it's currently still up to you as the application designer to prepare and maintain a cache of pinned buffers for use with memory copies to or from the CPU. Anyway, back to the beginning. So instead of using multiple tasks to overlap GPU and CPU computations, we can also overlap independent GPU operations. By just creating two tasks and performing GPU operations in each one of them, the GPU operations are going to be assumed independent, and the GPU may be able to perform these operations in parallel. This is actual parallel execution, not just concurrent. But it does depend on how powerful your GPU is and how demanding your application is. But in general, it may be very useful when you can't fully saturate the GPU with a single stream of operations. And that's an increasingly common thing with today's powerful GPUs. And again, let's look at the profiler. This is clearly visible here. As an example, I have defined a compute function that performs a matrix multiplication from the cuBLAS library, as well as a native Julia kernel by calling broadcast. And by calling this compute function from two different tasks, we tell CUDA.jl that these operations are independent and can be executed in parallel. And as you can see, the individual operations really are executed in parallel, with both the matrix multiplication and the broadcast kernels overlapping in the profiler trace. So again, I'm going to emphasize that CUDA.jl assumes that operations are independent if they are executed from separate tasks. And I'm going to briefly explain how that works because it also has some consequences. So essentially, CUDA.jl now maintains all of its state as task local properties. Each task gets to choose which device to work with and also uses a task-specific stream to queue operations on. And library handles like cuBLAS handles or cuDNN handles are also task-specific. All CUDA.jl wrappers now automatically use these task local objects, so as a result, all CUDA.jl functions are task local. And you can simply observe this by calling the stream function and doing so again from a newly created task, resulting in a different object. And behind the scenes, there's a ton of complexity supporting this. For example, we need to cache these objects and handles because creating them for every new task is very expensive. A lot of CUDA library state is also maintained globally, so we need to detect task switches and reconfigure the library appropriately and so on. But as I said, it also has some user-facing consequences. Namely that now you need to be careful when sharing data between tasks because tasks are using their own state. So if you allocate the GPU array on one task, you cannot just use it like that on another task because both tasks use different streams. You need to synchronize so that the data is ready too. But synchronization is itself also a task local operation. So you need to synchronize the task that allocated and produced the data. Here, that's the global task, so outside of the @async block. And of course, the same applies when you produce data inside of an @async block. You can't immediately use the data, but it's also inefficient to synchronize where you use the data. If it's not possible to synchronize in the task that produces the data, it is possible to perform a whole device synchronization by calling the device synchronize function. But that's a very costly operation. So not only does it synchronize all streams, even unrelated ones, but it's also an operation that blocks inside of CUDA, so we're not able to switch tasks. Again, the best and simplest option is just to synchronize within the task that produced the data. Another possibility is to use multiple GPUs. As I mentioned, each task can choose which GPU to work with, so you can just switch devices at the start of each one and expect both devices to be active at the same time. But again, there's some caveats. For one, if you're using multiple devices, it's recommended to explicitly switch devices at the start of each point. And that's because we currently have no mechanism to inherit variables from parent tasks, so the chosen device would depend on the order in which tasks get scheduled. And to prevent that, it's better to just call the device function at the start of each task. Another limitation is that CUDA arrays are currently implicitly device bound. That means you have to take care to only use arrays on the same GPU they were allocated on, or you will run into memory errors. However, both these are expected to get fixed in the future. And finally, with Julia's task system, it's also possible to use separate threads for every task. So here, by using the @span macro from the thread standard library, we can see that our multi-GPU example now executes on different CPU threads. And this can be useful when you want to perform heavy CPU computations that would otherwise starve the single-threaded execution, or when you have to call CUDA functionality that blocks in the CUDA library and prevents task switches. If you have every task run on a separate thread, that's no issue. Do, however, note that thread safety of CUDA.jl is a work in progress, so this functionality is pretty experimental. But if you have a use case that would benefit from threads, please try it out and let us know how it works or doesn't. So to recap this part of my talk, in CUDA.jl 3.0, we've made many operations asynchronous while introducing task local state. And this has made it possible to use Julia tasks for independent computations. These tasks are then executed concurrently, making it possible to overlap CPU with GPU computations or independent GPU computations, possibly even using different devices or multiple threads. You do need to take care though, because especially when sharing data between tasks or between devices, there's some caveats. So for the remainder of my talk, I'm going to briefly highlight some of the other important new features that we have in CUDA.jl 3.0 and later. The first one is a bit of an implementation detail, but the fix greatly improves usability. You now have a mechanism to register device override, GPU-specific methods that replace an existing implementation. For example, we can now replace the base sign function, which used to be GPU incompatible, with a CUDA-specific version. In the past, it was necessary for users to call CUDA.sign instead of base sign, but nowadays CUDA.jl can automatically perform these replacements. And this had fixed a lot of bugs, but it had also enabled a reuse of much more code, because we can, in a very fine-grained manner, redefine functionality with something that's GPU compatible. For example, we can use it to redefine the rand function. And CUDA.jl 3.0 comes with a GPU-compatible random number generator, and calling the rand function from within a kernel now automatically uses that RNG, and otherwise it behaves as expected. So with CUDA.jl 3.2, performance of the RNG and this functionality, as well as the quality of randomness, has been greatly improved. So if you want to use random numbers in kernels, I recommend using the latest version of CUDA.jl. Another important feature is the integration with the asynchronous allocator from CUDA 11.2. This is important for concurrent programming because allocations used to be synchronous, but it also improves performance because it enables us to get rid of the caching layer that we had developed, but also put a lot of additional pressure on the Julia garbage collector. As you can see, by doing so, we've noticed some significant performance improvements on realistic applications like AlphaZero and DiffyQ Flux. But still, it doesn't completely solve the memory pressure issue. And over time, your application might still be spending significant time in the GC. That means it's still recommended to help the allocator by calling unsafe free whenever an allocation can be freed early. And yet another CUDA API we now support is for creating computational graphs. So imagine you have an algorithm that requires launching many small kernels, for example, to perform some iterative transformation. Because those kernels are so short, and importantly shorter than the time it takes to launch the next kernel, the GPU is used pretty inefficiently. And you can see that by all the gaps in the profiler trace. And of course, the best solution here is to re-implement the entire step as a single kernel. However, that takes quite some effort, and it may even be impossible if you use complex operations like, for example, matrix multiplication. One alternative is to record the sequence of CUDA operations for a single step into a computational graph. and have future invocations execute that graph instead of executing each individual operation. And with CUDA.jl, that's now as simple as putting add captured in front of group of operation. And as you can then see in the profiler trace, only a single API call is performed to launch the pre-recorded graph, resulting in better CPU usage here. Do note that not every operation can be recorded in a graph. You can't, for example, allocate memory or compile kernels. Only relatively plain operations like kernel launches are allowed. And it's also not a magic performance bullet. It only applies to specific situations, and generally it's still better to optimize your individual operations instead. And finally, CoreArray now also supports so-called isBits union element types. So in this example, I store either an integer or nothing, and that kind of value can be represented inlined without requiring a pointer to heap allocated memory for every element. And that's the so-called isBits union optimization, which had been implemented in the base array type, and it's also supported by CoreArray now. And this feature may be an important step up towards GPU support for data frames, which heavily relies on these union arrays. So if you're interested, please try this out. I mean, we have the core functionality, but obviously a lot of operations in DataFrames.jl still assume a CPU array type, and that package would need to be adapted as well. So for more information on all this, do subscribe to the blog at juliagpu.org. Every couple of months we publish a blog post with new features in CUDA.jl and the other GPU backends. We also have, of course, the package documentation, which is admittedly a little sparse, but we do have a dedicated section on, for example, how to profile code, how to use tasks, and so on. Thanks for your attention. If you have any questions, feel free to ask them on Discourse or drop by the GPU channel on Slack or Zulip. Thanks.